So we have the forms phi1 and phi2. We know what its values, their values are on these two basis vectors, and we want to determine their values on the canonical basis vectors. That's not too hard, because you can make the following observation. So how can we combine the canonical basis vectors out of these two? The first one is simple. The first one is just E1 is B2 minus B1. 3,1 minus 2,1 is 1, 0. Now, how can we achieve the second basis vector? So how can we get E2 combined out of these two? Now, if I would have an audience, I would ask you the question and see who gets there first. But the idea is also it's not that too hard to see. It's not too hard to see. We take 3 times B1 and subtract twice B2. Then we have 6,3 minus 6,2, which gives 0, 1, which we wanted. So these are the combinations of these vectors. We will learn about general methods, how to solve such problems in the next section. So how to get some really systematic method of how to solve such equations. But yeah, this we will see. Now, this is what we have. So from this we can compute the values of the dual basis on the canonical basis. So phi1 is the dual of B1. This means phi1 of 1, 0 is phi1 of, by linearity, phi1 of B2 minus phi1 of B1. So by definition, this is 1 and this is 0, just because of this duality notion. This is also 0 minus 1, which is minus 1. Okay, phi1 on 0, 1 is then by linearity 3 phi1 of B1 minus 2 phi1 of B2. Okay, this is again 0, and here we have 3 times 1, so this is 3 minus 0 is 3. Same for phi2. Phi2 of 1, 0 is phi2 of B2, which is 1, minus phi2 of B1, which is 0, so 1 minus 0 gives 1. And finally, phi2 of 0, 1 is 3 phi2 of B1, which is 0, minus 2 phi2 of B2, so this is minus 2, so 0 minus 2 is minus 2. This means we can write down our basis vectors now, namely, dual basis vectors now. Phi1, x1, x2 is by our computation just this coefficient here minus 1 times x1, and we have plus 3 times x2, and phi2 of x1, x2 is in the same way. Here we have 1 times x1 minus 2 times x2. So this is the dual basis. Okay, this is actually non-obvious because like, if you take a look at these vectors, maybe it's not that easy to see that this would come out. So this is really some nice little computation. Okay, now so much for an example. Now, one property of the dual basis is that there's a nice connection between these dual bases and the matrix representations of bases, of linear maps with respect to bases. So we take two finite dimensional vector spaces V and W. Over K, and we take a linear map from V to W. Okay, and we have bases of V and W, so B from B1 to Bn. As in the previous section, let n be the dimension of V, so this is then implicit in there. Ordered basis of V, and we take C with vectors C1 to Cm be an ordered basis of W. So then the matrix MBC of F, which represents the map F with respect to the coordinates defined by B and C, this has the entries A, I, J, and now comes the interesting part where, so how are the entries of the representing matrix given? They can now be formulated as follows. A, I, J is the same as the dual vector, so the covector Ci star, which is a linear map from from W to K, and we insert f of bj, which is an element of w. So this is indeed well defined. This goes, f goes from v to w, this goes from w to k, so this is a well-defined map. It's a well-defined number that's in here. So this is how we get the entries. Now, how to see this? In the following way. So that's, yeah, we have the aij defined like that. So we know just by theorem A20, that was the effect of representing matrices on bases. We have seen that f of bj is the sum from 1 to m over aij ci. And this holds for all j between 1 and n. But if we have this formulation here, we get that, I need to have a different name. Sorry, I is already given for the index here. Let's call this sum over k, so a kj ck. This is the effect of the representation, of the matrix representation. And now this means if we apply this covector, ci star to f of bj, this is ci star of the sum k from 1 to m, a k j c k. But by linearity of these covectors, this is the same as the sum from 1 to m, a k j ci upper star applied to ck. And there we have it, because we've seen this is just by definition of the dual basis, this is the Kronecker delta. So this is the sum from 1 to m, a k j delta I k. Yes, exactly. And here we see that this is only, delta ik is only non-zero if I is equal to k. So almost all summands are vanishing, and the only thing that's left is aij times 1, so aij. And this is what we wanted to show. So this holds for all I between 1 and m. And this already proves the theorem. So that's a nice little relation between dual bases and these matrices, which will come in handy at a later point. Now, what can you do with dual spaces? So there's a crucial property, which is maybe the most important property that we will need here about dual spaces. So let V and W be arbitrary vector spaces over K. Then let F be a linear map from V to W. Then we can define another map, namely the map F upper T, which is now going between the dual spaces, but in the opposite direction. From W star to V star, namely as follows. Ft of a map phi, so this is a covector, this is a map from W to K. Now we turn this into a map from V to K by phi composed with F. Since F is linear, this is a composition of linear maps, hence linear. So this is really going from V to W to K, right? So just to give you the schematics here, before we had a map from W to K, which is phi, and now we just put something in front. We just put the F in front here, which goes from V, so the composition goes from V to K, and we're happy. So this means just for each such phi, we just put F in front. So this is kind of this dual thinking, which is a bit mind-twisting if you see this at first sight, but you just have to get used to these things. It's not that hard once you get the idea. Well, wasn't the chair bumping in the other room? Sorry. No. Anyway. Okay, so this is how we define the map. And this map is called the transpose of F. So crucial is really that F is going into the opposite direction. F upper T is going to the opposite direction than compared to F. This is really important because, like in physics, you have this notion of contravariant and covariant tensors. This is basically where the dual spaces are underlying. So especially with which linear maps go in which direction and how you can transform coordinates. This you will later see in your physics classes, for example, in quantum mechanics. there you have the notion that I think Dirac's formalism originally of bra and ket vectors. And these bra vectors that you have there, they are actually co-vectors, so they are elements of dual spaces and popping up there. So in quantum mechanics, you will handle dual spaces all the time. And in general relativity in particular, there you made a lot of use of tensor calculus. And there you have these contravariant and covariant tensors, and this is basically also what's underlying there. Sometimes you have dual spaces, sometimes you have vector spaces, and so depending on in which direction some coordinate transforms are induced. This is basically the whole mathematics underlying this, and this is also the reason why I'm doing this in detail in this course, because you will need this for certain in your later on physics classes. Anyway, so this is well defined, as I said, the composition of linear maps is linear, this is all fine. Now let's check for some properties. So theorem 845, yeah, again, V and W vector spaces over K, and F be a linear map from V to W. Then, first of all, the transpose, which goes from W star to V star. This is now again a map between vector spaces, and this is linear. So if I take the sum of two covectors, the value of F on this is the sum of the two. So this is all, again, linear. And B, if X is another vector space over K, space over K, and G is a linear map from W to X, then, yeah, need some more space, then now I can define the composition G composed with F, which is now a map going from W to X, and I can take the transpose of this map. So this would now go, I need some more space, from, so this is a map from V to X, so the transpose is going from X star to V star. And this is the same as, and now we just have to invert the order, Ft composed with Gt. Right? So you just need to keep in mind which order you have to do. So just as a scheme here, if we have some map going from X to K, some covector phi, so if we have first V and W, and we have F and G going in there. So if we start with this phi and put this composition in front, the first thing we need to do is, if we want to do this individually, first put G in front, which means that we first apply, so this, of course the order is a bit confusing, this means first applying GT, so first put G in front of the map and then put F in front of it. So this is why this order becomes, this is a bit confusing, but this is just the other way around in this setting. Okay, this is the part B of the theorem, so proof. The linearity is really not very exciting, so I want to skip this proof. So A is proven in the lecture notes. So this is basically also, yeah, you basically do exactly what you would think you would do. Nothing very important. And for B, we just do this argument I just gave you with hand waving and arrows here, just do this formally. If we take some phi in X star, we just do the formal definition, G composed with F transpose applied to phi. So this is by definition putting this in front. So this is phi composed with G composed with F. So I just put in the parentheses here because now it's kind of clearer what happens. Now, as we know, the composition is associative. So this is the same as putting the compositions and the parentheses in here like this. So first G and then F. So this object that's standing here, this is GT of phi as a map composed with F. And this is now by definition F transpose of G transpose of phi. And this is what we wanted to show. So this is actually just elementary arithmetics. It's just a bit confusing because kind of like the directions are inverted half the time. Okay, so much for that. So the question is now, what does this all mean for matrices? Namely in the following way. Maybe, let me get the idea, sketch this schematically here. Namely, assume we have, again, F goes from V to W, linear map, and V and W finite dimensional, which is our most interesting setting here, finite dimensional. So if we have a basis of V and a basis of W, B ordered basis of V, and C be an ordered basis of W. So then, first of all, we can form their dual basis. So B star and C star, their dual basis. So B star is a basis of V star, C star a basis of W star. Okay, then there's a simple question. Namely, what is the relation, or how are two objects related? Are one object and another object that I'm going to fill in related? This is now the interesting question that we are going to tackle. Namely, first of all, we have V, we have bases, so we can compute the matrix representation, MBC of F. On the other hand, we have the transpose of F, which goes now from W star to V star. They are both finite dimensional as well, of the same dimensions, and we have the dual basis there. So we could also form the representation matrix of F transpose with respect to the dual matrices. Again, we have to change the order, so we just go from first C star and B star of F transpose. So, since this relation of dualing and so on, I mean, this is the same map underlying this, and there's no question, okay, these maps, you might expect somehow, this is what you would intuitively say that they must be somehow related. So somehow if you know the one matrix, you should also be able to know the other, because it's basically the same thing with arrows turned around. So the question is now, how are they related, or are they really closely related? And it turns out the answer is yes. So it's very, in some sense you can, there's a nice explicit relation, and this is what we're going to explore next. But before this, we kind of need to find an equivalent of these transposing, how we define this, in the world of matrices. So how can we do a similar thing for matrices? What has the same effect there? And this we shall see after I erased. Okay, what does transposition look like in the world of matrices? Let's do a straightforward definition, and afterwards we will see that this really is what we wanted, or that this kind of does the nice thing we were searching for. So assume we have M and N in N, and assume we have an M by N matrix, whose entries I want to call Aij as usual. So this is an M by N matrix. With entries in K. Now, we assume the case that we have in mind is that we have a representation, a matrix representation of a linear map from an n-dimensional space to an m-dimensional space. This is an M by N matrix. Now, the transpose of such a map would go into the other direction. So this means this would then go from an m-dimensional space into an n-dimensional space. So just the other way around, with rows and columns in this case. So the transpose, which then should do the job that we want. The transpose of A is the matrix AT, so where the rows and columns, the numbers have to be reversed. So this is an N by M matrix. I wanted to name these entries, sorry, AT, and the entries are just Aij prime. Sorry, AT is the name of the transpose matrix, and I want to call them. So Aij prime. So how are the Aij prime, how do they depend on the Aij? I mean, it's kind of how can you turn these a matrix with m rows and n columns into a matrix where it's the other way around? And the idea is kind of the simplest thing, you just flip everything. Namely, A prime Ij is just Aj I for all I and j. So this now for all I between 1 and n, j between 1 and m. So that's it. That's the simple answer, and this will turn out to be the analog of transposition in the world of matrices. Now, what does this mean concretely? Let's do some little examples so you can easily see. I mean, this as a formula, this doesn't look very intuitive, but once you see the example, you will think, okay, that's what it is. Now, take an example. So let's have the complex numbers in here for a change. So let A be the matrix 2, 1, 3i, and 4, 7i, 5. This is now a 2 by 3 matrix with complex values, 2 rows, 3 columns. So what does AT look like? AT is now 3 by 2 matrix, so 3 rows and 2 columns. And this just means flipping the indices. And this means here the first row becomes the first column in the new matrix, and here the second row becomes the second column. So this is what transposition does. Rows becomes columns, columns become rows. So just the other way around. Which means in this case, AT is the matrix, so we just flip, we make this into a row, 2, 4. Second row is 1, 7i, and here we just get, 3i, 5. Yep. So just flip everything like kind of by the diagonal, so to say. This is how we can achieve the transpose. So converting rows into columns and vice versa. Second example, now a trivial example almost, but this is something you should keep in mind, or that we will also need in a bit. For each n in n, if we take the identity matrix of size n and take its transpose, what is the transpose of this? I would now ask the audience. If you take a look, there's only ones on the diagonal, and if you kind of flip rows and columns, you see that the diagonal remains unharmed. Nothing's happening to the diagonal. So the ones just remain, and everything else is just 0. So whatever I flip, I get 0 again. So the identity matrix, the transpose of the identity matrix is just the identity matrix. Nothing happens about transposition. This also happens, matrices with this property that the transpose is the matrix itself is called a symmetric matrix. We will need this later on. But for now, we don't study them in detail. Instead, we go on to the connection between transpositions of linear map, or transposes of linear maps and transposes of matrices to do what I promised now. So let VW be finite dimensional vector spaces over K. Oops, vector spaces over K. We take bases, so B an ordered basis of V, C ordered basis of W, and we consider their dual bases, B star and C star, their dual bases. Dual bases. Okay, then the matrix representation of F transpose, so between W star and V star with respect to the dual bases, C star and B star, this as a matrix is simply the transpose of the matrix representation of F with respect to B and C. So matrix of the transpose is transpose of the matrix, so to say. So this really works. So this is the reasonable definition for a transpose in order to mirror this construction for linear maps. Okay, how can we see this? This is a nice little computation. So we put, just to abbreviate the notation, A is supposed to be this matrix representation MBCF. So we call the entries A, I, J. And the other matrix we call A twiddle or A tilde, where the entries are just called, the entries are also called A, I, J twiddle. So this is supposed to be M, C star, B star of Ft, and we have to show that the A tilde is the transpose of the matrix A. This is what we need to show. Now, missed. Sorry, I need to name these vectors, of course. B, as usual, is B1 to Bn. C is C1 to Cm. Sorry, hope still readable. So, as usual, we name these vectors. Now, by definition of these matrix representations, by the, so we have seen that the matrix representation encodes the effect of a map on the basis vectors. So in this case of the transpose, it looks a bit odd, but this is what this theorem says. So that was theorem A20 again. this means in the case of the transpose, if we apply the transpose map to Ci upper star, so the ith vector of the dual basis C star, this is the sum from k from 1 to n this time, and now the matrix representation of ft, which was this a tilde, so we have a tilde ki, sorry, times bk upper star, which was the kth vector of this basis b star. This looks a bit odd, but this is just this formula. So this holds for all I between 1 and m. Now, we can now use the computation from the previous theorem about matrix coefficients. Is it still there? No, this is only had before. How the matrix coefficients are, or the matrix entries are computed by the basis and the dual basis. Namely, the following. By theorem 843, for all I in 1 to m and all j between 1 and n, we get that the coefficient now, if we go back to f instead of the transpose, aij. This we saw, that was content of the theorem. This is Ci upper star with evaluated on the vector f of bj. Okay, now this what's actually standing here. This is Ci upper star composed with f applied to bj, but this here is the transpose. This is ft of Ci star. Now it's a bit messy with the double parentheses. This is now a map in v upper star, so you can insert a vector of v into this map, which we shall do. Namely, this is this evaluated on bj. And now we can use this formula. These are all maps where I can insert vectors. So by this formula here, let's call this star. So by using star now, this is the same as the sum from k equals 1 to m, a tilde ki, bk upper star in bj. And now we can use the definition of a dual basis. This is just the sum k from 1 to m, a tilde ki. And now here we know that, so bk upper star evaluated on the base vectors, we know that it is 1 on bk and 0 on all others. So in this Kronecker notation, this would be delta kj. So this means almost all of these summands are vanishing. The only thing that's left standing is the one where k is equal to j. So this means this is simply a tilde ji. And this is what we wanted to show. Just the indices the other way around than there. But this means, this implies that a tilde must be the transpose of A, and this is precisely what we wanted to show. These are the two matrices that are computed here. So this is just an explicit computation of just inserting things and juggling the dual spaces correctly. Okay, now, so we've seen this nice property that this transposition map then reflects the transposition we had before. Now, for the transposition on matrix level, there we haven't seen much. We just have seen the definition and the nice property here. But we shall now explore some properties, because basically the same properties that hold for the compositions and the transpositions hold for transposes of matrices and matrix multiplication. I'll summarize them in the following. So theorem 849. So let L, M, N be natural numbers. Now, for all A to be an L by M matrix and B to be an M by N matrix. So this means this has the same number of columns that this has number of rows. So we can define A times B, the matrix product. So the question is now, what's the transposition of a product? Before we've seen that the transposition for linear maps of a composition was the composition of the transpositions, just the other way around, and it's precisely the same here. This is just B transpose multiplied with A transpose. Keep in mind, the matrix product is not commutative, so this is really not, you cannot just change the order of multiplication here. Okay, so much for that. Then B, this is something which is less obvious. For A be a matrix in GLNK, so an invertible n by n matrix, the following holds, that the inverse of the transpose matrix. What's the inverse of the transpose matrix? This is simply the transpose of the inverse matrix. So this was originally the inverse of A, and we can just transpose this one. So this is just, yeah, this commutes basically these two operations. So, yeah, and finally, for all A to be in some m by n matrix in K, we get the following property. The rank of A, which we studied before, is the rank of A transposed, which then shows that the same holds for the map. So the rank of a map is the same as the rank of its transpose map for any linear map, but this we won't, I'm not mentioning explicitly here, but this is the property there. Okay, let me erase and then prove this. The proof of part A is just a straightforward computation of the different entries. For this purpose, we let A, so this is part A, let the entries of A be the Aij. We denote the entries of B by Bij. Okay, and we put C to be the product A times B and denote their its entries by Cij. Okay, now we have the transpose matrices in there, so we need names for them as well, which is a bit tedious, but anyway. AT, I denote the entries as Aij prime as a written definition. So of course this is the same as Aj, but to get this a halfway coherent computation, we give these extra names. The coefficients of the entries of Bt are Bij prime, and the entries of Ct should be called Cij prime. A lot of bookkeeping here. Okay, so now by definition of the matrix product, we know that the entries of C are given by Cij is the same as the sum k from 1 to m Aik Bkj. That's the definition of the matrix product. Now, this means that for the transpose, we know that Cij prime, Cij prime. So this is by definition just of the transpose just Cji, so just the other way around. And this means that by this computation, this is the same as the sum from 1 to m Ajk Bki. Okay, now we need to compute the product of Bt and At and see that these entries are the same to show that, yeah, this works. So we put Bt times At. There we name the entries Dij. So we need to show that Dij is the same as C prime Ij for all I and j. So then, using again an unreasonable amount of space. Yeah, anyway. So by definition, this is the matrix product of Bt and At. So this means Dij is the sum from k equals 1 to m of the Ik entry of the transpose of B, which is Bik prime, times the Kj entry of A transpose, so A prime Kj. But by definition, this is the same as the sum from 1 to m as, so by definition of these entries, Bki times Ajk. This is of course the same as the sum from 1 to m Ajk Bki. And we have just computed that the Ci prime are precisely the sum and that this holds for all I between 1 and L and j between 1 and n. So this means C transpose is Bt times At, which is exactly what we wanted to show. Okay, Basically just bookkeeping, nothing very exciting going on here. So part B for the inverse, there we just need part A in a smart way. Namely by A, we know that, so we need to show that this map here, the transpose of the inverse, that this is really the inverse of the transpose, which means this multiplication and the other way around, they both have to result in the identity. That's the property of the inverse matrix. So here we see, but by A, this is a product of two transpose matrices. So by just using this relation in A, this must be the transpose of the product of the two, but just with different way around. This is A minus 1 times A t. But this is the inverse, so by definition this is INT, and we've seen in the example before that this is the identity matrix, so this is the property we need. And in the same way, A to the minus 1 transpose times A transpose. So the other way around, this is now, by using the property again, this is A times A minus 1 transpose, which is again, since this is the inverse, IN transpose, which is IN. So this shows these two together. AT to the minus 1 is the inverse of the transpose matrix. Okay, not very exciting. So part C, we need to show the rank of the transpose is the rank of A. And then we will need the nice matrix property that we had before, that R be the rank of A. So then, if this is the rank of A, then by the previous corollary, that was this, this standard form of matrices. So we can always write, make the matrices into into the simple form where you have the identity in the top left corner and zeros everywhere else. So by formally by corollary 836, there are matrices S in GL MK, T in GL NK, such that, sorry, I made a little mistake. So there are S and T such that A times S times T to the minus 1 has as a block matrix this nice form that in the top left corner we have the identity matrix and the rest is filled up by zeros. So this form, but this now if we take the transpose of this on both equations, of course two matrices coincide if and only if the transposes coincide, that's obvious from the definition. So this means that the transpose of this is the transpose of SAT to the minus 1. But if we take a look at this, as we've already discussed, the identity matrix transposes itself, and everything else here is filled up by zeros. There are some ones on the diagonal of that matrix, or in this, and everything else is just zeros. So this is the same as its transpose. This means we have, if we now apply part A to the right-hand side of that equation, we get that, so if we apply this twice, we can first flip these and then these. This is kind of by just iterating this. This means that T to the minus 1 transpose times A transpose times S transpose is the same as this block matrix IR 0, 0, 0. Okay, but then we've seen for this purpose, because this is now AT and these are now isomorphisms, this implies, by result from the previous section, which I don't have in mind at this point, but that the rank of AT is the rank of this here, because these are two, these are in GL, N, or M respectively. This is the same as the rank of T to the minus 1 T, A, T, S, T, which is obviously R, and this is what we wanted to show. So the rank of the transpose is the rank of the original matrix. Now one last corollary, which is not very exciting to look at if you see this now, but this will be actually pretty useful in the next section. We shall see the application of this later on. So that A be an M by N matrix, K, and now we denote its row vectors by A1R. Let me just add this R so not to confuse it, because otherwise it was always columns that were denoted like this. These are A1 to AM to be the row vectors. Of A. Then it turns out that the rank of A is the dimension of the linear subspace spanned by the rows. We had the same property for the column vectors. This is what we saw for the rank, but it turns out it's the same for the rows. MR, yeah, like this. So, in other words, the maximal number of linearly independent rows. Of A. And the proof is very simple. Let me just summarize this. We have seen that rank A is rank A transpose, and the rows of A are the columns of A transpose. And then we've seen in theorem 849 that the rank is just the maximum number of linearly independent columns, so this is just by flipping rows to columns. Okay, we'll see in the next section what this is about, and this is now kind of finishing the dual space in the abstract situation. We will get back to them later on. Now, in the next section, we will do a bit more concrete computations, and we will finally learn how to explicitly solve systems of linear equations. And this has several applications. First of all, we can also compute inverses of matrices by some explicit method, and we will do really a lot of computations, and in the exercises there will be actually numbers for a change, and so yeah, this is what we will see. So from the theory now get back to computing things. And we will see that how we can use matrices for this, and how you can use the formalism of matrices and the matrix products and so on to get the convenient, to do the convenient stuff there. Okay, see you in the next section.